okay, and a possible problem we can attempt solutions to. Okay. So we agreed yesterday that a gaseous and less populated spherical star is used to formulate most of the expressions we get in general relativity with respect to astrophysics. And we also agreed that there were other models that were postulated, and those models could not address the possible questions that arose due to lack of a strong mathematical background. And we equally said that other models were not based on general relativity. Okay, so the model that is based on general relativity is the Rabonsky and Borisova metric. Okay, I was happy some of you are able to get the book Inside Stars that has detailed the method they used in getting that. Actually, that book is very rich. It's a very rich book. With that book, you can do a lot. You can do a lot. Because if you go through that book, you will discover he has used general relativity to even classify stars. He has used general relativity to classify stars. Okay? So if you want to work with neutron stars, the metric tensor is there. If you want to work with dwarfs, the metric tensor is there. If you want to work with regular stars, the metric tensor is there. Okay? And there are so many things that are being done there. So it's a very rich book. But you need time to digest it. Okay? So we will not go deep into most of the things that are done there. Okay? Our ABA is just to motivate you. Okay, and then we start doing something that can lead you somewhere. Okay? So as we said yesterday, we said we are going to look at Borisova and Rabonsky metric. Okay? So the line element in that case is of the form ds squared equal to 1 over 4 into, this is a cube root, cube root of 1 minus rg over a minus the square root of 1 minus r squared rg over a cube. All of that squared, c squared dt squared minus 1 minus r squared rg over a cube to the power minus 1 dr squared minus r squared into d theta squared plus sine squared theta d phi squared. I prefer black. I hope you bought new black. Okay. So this is the metric tensor, or the line element for Borisova and Rabonsky. Actually, Borisova is a female, and Rabonsky is male. Well, Borisova is more elderly. She's getting to her 80s now. Okay? She's getting to her 80s now. So, it looks similar to what we have been seeing, is that not? It looks similar to what we have seen before. You will discover that G22 and G33 are the same to what we had earlier. The only difference here is G00 and G11. That's the only difference. Okay? And RG is what we call the Hilbert radius. Okay? RG is the Hilbert radius. Okay? Which is just simply 2 GM over C squared. Okay? And then our A is just the radius, or the physical radius of our star, of our mass. Okay? It can either be a star or it can be any other mass. The R, which must be greater than A, is our radial distance. Okay? And R must be greater than A because we are dealing with an exterior metric. Okay? If the radius is A, then R must be greater than A because we are working outside the sphere, outside the mass. So R must be greater than A. Okay? R must be greater than A. So this is our metric, our line element. Remember, this is the same as most of this black. Most of this black is finished. Okay. Okay, the red will be better. Okay. It will be better, but it will not be good for our eyes. Okay. So we have that. We have that. Okay, so this is this the first time are you seeing this? Uh-huh. Which is? It's also a distance. It's the proper distance. The proper distance. Okay? It's a proper distance. So we have that. So this is the proper distance, or the proper time interval. Okay, so from here, we can easily get our G00. Is that not? So our G00 will just be 1 over 4 into the cube root of 1 minus R, Rg over A minus the root of 1 minus R squared Rg over A cube. Okay. So some of you can go back and try to read on how this is being derived. Okay, but that is not our concern for now. Okay? That's not our concern for now. So we are standing on the shoulders of giants to see far. Okay? So we'll just stand on their shoulders to go further. We'll not go back to this. But you can take time to go through it and see how they came out with this and the convincing reasons they gave for this. But so far, what we want to do is just to stand on their shoulders and move further. Okay? Okay. So this is our G00. Our G11 is, if you like, you can maintain the minus. If you like, you can leave the, so it's the same as 1, I think 1 minus r squared r, rg over a cube to the power minus 1. Then our G22 is just r squared, and our G33 is r squared sine squared theta. Okay? So this is our metric tensor. All other components are 0. Remember, we are expected to have up to 16 components. Okay? So we have only 4 non-zero components. The others are 0. So when we have this, our task is to get Einstein's field equations. That is our task, to get Einstein's field equations. We already have the metric. So we now need to get our G alpha beta. Okay? So we'll move from this step. So the first thing we are going to get is our G alpha beta. That's the first thing we're going to get. Are we together? So after getting our G alpha beta, we'll now also get our gammas. Okay, alpha, beta, that. So we'll get that. And when we get that, we'll now move to our Riemann-Christoph field tensors. After getting our Riemann-Christoph field tensors, we'll get our Ricci tensor. And after our Ricci tensor, we'll get our curvature scalar. Okay? And after our curvature scalar, we'll get our Einstein tensor for that gravitational field. Okay? We'll get our Einstein tensor for that gravitational field. So, the right-hand side of Einstein's equation is forgotten the constant here, T alpha beta. So this will be our field equations. So there are two things that can happen when we get our field equations. Okay? The first thing we can decide to do is to assume that our star is placed in empty space. And the only thing contributing to gravity is the mass within the star. Okay? Then the right hand side will be 0. Okay? The right hand side will be 0. Another thing is we can look, because this stress tensor, there are many definitions of the stress tensor, depending on the medium in which you are working on. You can have a perfect fluid, you can have other type of media. But the easiest problem is when you place your star in empty space. Okay? Their life is a bit easier. So you place your star in empty space and equate the right hand side to 0. And then we attempt solutions. So we expect there are 16 equations, but we might end up with just 4 or 6. Okay? We might end up with just 4 or 6. So once we have those equations, we can solve one of them. So if you want to go a step further, you can decide to look for a stress tensor and fit on the right hand side. Maybe you assume that your star is placed in a perfect fluid. Then you look for a stress tensor for a perfect fluid and insert here. And it gives you a totally different equation, which you also try to solve. Okay? So that is our first objective. So as I said, I also expect you to review existing gravitational field equations exterior to spherical stars. Okay? The first one that we have seen is Schwarzschild's. Okay? We did not go into Schwarzschild's field equations. They are there. You will see them. I also have about 4 or 5 that I have also solved. You also see them. And many others. Okay? So you will see them. So once you have those field equations, you put them at one side. So in literature, you will get more than 100 field solutions. More than 100 of them. Okay, but for now, we will need just around 50. So you get them and keep them. Appreciate what has been done, and then you now try to do yours. And try to compare what you get with what is existing. Okay? And as you are trying to do that, you will now also appreciate the contribution of the plasma nature of the star to the field equations. Okay? You will now try to appreciate how your own is different from their own. What is the nature of the star contributing to the field equation? Okay? So you will have gotten something new that does not exist. And then you have added to the body of knowledge. Okay? So that is the first thing you will do. Okay? There is one of the field equations we solved, I and Professor Owusu. Okay? And that the solution is a gravitational wave. The solution is a gravitational wave. Okay? So you see so many of such. You see so many of such. So this is our first research objective. Okay? Then the second one, the next slide. Okay, the second one, we'll now derive the field equations interior. Okay? The field equations interior to the star. Let's imagine there is a particle moving within the star. How will the field equations look like? Okay? So we also have an interior metric. This is an exterior metric. We equally have an interior metric. So if you go through that book, Inside Stars, you will get the interior metric. So you get the interior metric, and you go through the same procedure. Exactly the same procedure. But this time you are within the star. You are not exterior to the star. So you now need to assume whether your star is a perfect fluid or not. Okay? The right hand side cannot be 0 in this case. Because if the right hand side is 0, then you are assuming that there is nothing inside your star, which is wrong physically. Okay? So you now need to make some assumptions. Maybe your star is a perfect fluid. Then you use the metric, the stress tensor for a perfect fluid. And you solve the problems. Okay? So that is the second thing we can likely do. The next one, please. Okay. Okay. So another thing we can do is to study planetary motion in the vicinity of such a star. You can study planetary motion in the vicinity of such a star. Okay, so what we did on Wednesday, trying to get planetary equations of motion. So you follow almost the same steps to try and get planetary equations of motion for this particular metric. Okay, so you try to get planetary equations of motion, and then we also try to solve them. So you follow almost the same steps. You start with the aligned element, and so on and so forth. Okay? Maybe you divide all through by the tau squared, you have T dot, you have all of that. And then at the end of the day, you now have an equation in terms of U. Okay? You have a planetary equation in terms of U. And then you will now look at your planetary equation and compare with other planetary equations that are existing in literature. How is your own planetary equation different from their own? Okay? What will happen to your own for it to reduce to Schwarzschild? Okay? What will happen to your own planetary equation for it to reduce to Schwarzschild? What will become 0? What will become infinity for your own planetary equation to go back to Schwarzschild's own? Okay? So you appreciate your own planetary equation with respect to other planetary equations that are existing. And then you also try to solve the planetary equation. Remember, when you solve Newton's planetary equation, you come out with a conic section. Okay? When you solve the one in Schwarzschild's field, you come out also with a conic section, but you now have a precision. You now have a precision. Okay? You now have a precision. So you also try to solve your own and see the nature of your precision, how it will look like. Okay? At one point, you can even calculate your precision and calculate that of Schwarzschild. And then look at the one that is observed, that is astrophysically observed. Okay, maybe using astronomical telescopes. What is this precision that has been observed? And then what did you calculate with your own solution? What comes out from Schwarzschild? Then you try to see, is your own closer to the observational, the one that is observed, or is your own further away? And you try to give reasons. Okay, you try to give reasons for that. So that is the second thing that can be done. And again, as I said, there is need for review. There is need for review. Okay? So you review other planetary equations that exist for this particular problem. And then you now try to compare your own to that one. And it may amaze you that each of these is a whole thesis. Okay? Each of these is a whole thesis. Okay? Each of these objectives is a whole thesis. It cannot be like that. You are using a different metric. You are using a different metric. But there are conditions that you can impose that will make your own to reduce to an existing metric. Okay, there are conditions you can impose on your solution that will make your solution to look like what is already there. Okay, so you cannot get the same. You can't get the same. Are we together? Mm-hmm. You can also study the deflection of light, which we did yesterday, using this metric. Okay? You can also study the deflection of light and try to see how your own deflection is different from those that are existing. Okay? So you can also study that. The same steps, although the mathematics might differ a bit depending on the problem you have at hand. Okay? And that is why it's good to go through literature. Because once you go through literature, you can have an intuition of what somebody is doing that can guide you to also do your own. Okay? Somebody might carry out an approximation, and you may need a similar approximation in order to move forward. So that is what can also be done. But remember, in this time around, you remember that light moves along a null geodesic. Light moves along a null geodesic. So you follow a different path altogether. Okay? So again, we can also investigate the effects of the plasma nature of stars on some gravitational phenomena. Okay? And the ones we saw in this, our study, were length contraction, time dilation, and spectral shift. Okay? So you can also try to do that for this field. You can also try to do that for this field. Okay? Okay, this one is a bit more involved. This one is a bit more involved. Okay, where you now need to bring in the effect of charges. Okay, you now need to bring in the effect of charges on your metric. If you look at Professor Owusu's books, there is a way you can combine an electromagnetic field to a gravitational field. There's a way you can combine the two. Okay? You can combine the two, and then you get a new metric that will describe the nature of charges and the nature of masses. So you can combine the two and then try to also appreciate what is happening. Okay, and actually all what we have been saying, you can do that for charged particles. Okay, you can do all what we have been saying from 1 to 5. You can do that for charged particles, because once you bring in charges, the metric tensor is a different one. Once you bring in charges, the metric tensor is a different one. So you can get totally different field equations, you can get totally different planetary equations, and so on and so forth. Okay, so you see there is quite much to be done. Okay, there's quite much to be done. So, but I think since we have agreed to have just 2 groups, so we'll address just 2 of those objectives. Okay, we'll address just 2 of those objectives. Since we have just 2 groups, so we'll address those 2. If we can address those 2 very well, then we can, even out of this place, we can also address we can continue working and address the other 4. Okay. So, as I said yesterday, so after the groupings, you will be the ones to stand here. I only sit behind there and observe and make inputs. Okay. So is there any question? Any question? Any question? There's no question. I don't know whether Prof is ready.
Just once, 2 minutes.
It's okay, sir.
after the foundation course, he was so interested in the area, and he started applying for scholarships. He just got a scholarship this year for Chinese Academy of Sciences. Okay, and he's telling me that tensors are troubling him. Okay, that tensors are troubling him. Okay, so, as I said yesterday, this our small gathering can be a springboard for you to excel. So please don't take anything here for granted. Don't take anything here for granted. Okay? drink root. Root is beer. No, I'm just telling you because the same process they use. It's a local fermentation of guinea corn. Is it not? What do you call it? Flour. When you ferment it, then you boil it. The fermentation gives it alcohol. Even like the alcohol you do from it, you can leave it for a while. For 3-4 days, it's fermented, is it not? You make it. Why is it that when you take it when it's very hot, it intoxicates you? Have you ever bothered to ask yourself? It's alcohol. No. I drink it. But I take whiskey. I am. You see? Just put this off first. Let me talk. You know, every day in your life, you need at least 1 tablespoon of alcohol. You might not drink it directly. You get it from the food you eat. Like if you make hot eba in the afternoon and eat it, why do you sweat? The alcohol is reacting in your body. Don't you know? So I was telling them this board, you can get alcohol, clean it, use area and wash it, dry it, your board becomes new. So you see the usefulness of alcohol. Why do our parents dry our cassava and yam under the sun? As they are drying, that water that goes off, which is a part of the CH0 group, those of us who did chemistry, contains the alcohol. They go off so that the children can eat without getting intoxicated. Don't you know? You people are here. Okay, good morning, everybody. Well, I slept yesterday because I needed to rest. Yes. Well, this morning we will try to look at Introduction to Mathematica. Now, you see, in theoretical physics, you need elements of numerical computation. The values like in astrophysical environment, for example, the rho, which is the density, is very small most times, or you can also get powers like the temperature, 10 raised to power of 6, 10 raised to power of 20 is very large. You cannot do it by manual, so you need computational techniques. There are some equations you will get, differential equations you will get, partial differential equations, systems of equations, and the only way you can get a solution and a clue to go on is by looking at numerical computation. There are several techniques, and there are also packages that will help us in doing this. It depends on the school where you are coming from. I came from a school where my directors in the early 90s started developing Mathematica, and I keyed in as a student of Mathematica.
So I use Mathematica. You will appreciate it. Mathematica, it was developed and is being modified by Wolfram. They are using it as Wolfram. It's all over. It competes with Maple, with MATLAB, and others. These are what we call algebraic software. They are what? Algebraic software. It's a system you can use doing mathematics with computers. When you come to computing, there's a garbage in, garbage out. It is not the computer that does the work for you. Rather, you direct the computer. You direct it well. It gives you the required results. All right? So, Mathematica is one of the algebraic software that are used. Most professionals use them. It's engineers that actually prefer to use MATLAB in their simulations. I prefer to use that because it helps me to do some dirty jobs. If I need to have an analytical expression of my solution, I can get them in Mathematica, which you may not likely get in your MATLAB. It's only numerical computation it does for you. So, Mathematica is a software. There is an edition for students. It's very cheap. You can buy Mathematica for students. You want to buy the professionals, they go from between $5,000 and above. It's expensive software. Your universities can buy if you are ready to use. Okay. Now, as I said, Mathematica is an immense computational software. It's what? A computational software. Being a computational software, it helps you to do mathematical computations and expressions with your computer. So it helps you to do this with your computer. Now, in this class, because we may not have enough time to go through, I may have a lot of literature, books I will give you that will guide you. As long as you have the software, you practice them, you become an authority. At the end of today or thereabout, I can send some of the books to the organizer, and then which you will have. And little by little, you begin to develop your skills in Mathematica. It's a matter of interest. Okay. Now, we will focus on some tools. Our focus will be on some tools. Some tools and skills. These are things we might try to get from this particular class. Mathematica can be used as a calculator. It can be used as what? A calculator. And it uses commands. You will command it. So it is what you tell it to do that it will do for you. The library is so vast. At times I may be solving some problems I don't know how to do. You can, if you have a licensed Mathematica, you can link your problem online, and then people who are working in that can assist you. But if you're not online, forget it. They will clamp you. You can't use it again. So that's why it's not good to have a cracked version. Okay. Now, we will look at some basic commands. Aha. Which, can I have this one? We have some commands we need to when you give a command, how does the computer execute it for you? That is the first thing we will try to do. We make use of shift and this to execute our command. Our command. For example, if you look at here, I have 5 times 7 minus 32 divided by 6, all of this divided by 4. If you write that it's a command that I want to do simple arithmetic, if you press down the button shift at the same time with enter, it will execute to give you this is output. So you can see this is the input. Automatically it does it for you to give you that answer. 89 over what? 12. But giving you this, you will see that you still have something to do. It's in fraction, is it not? But you will need it to be in decimal, or to be either you want the decimal to be chopped off or not, but you need a whole number solution. But it happens that that thing gives you a fraction, and for you to reduce it to an appreciable number you have to get to another line of instruction, which you can now see is a input 2 percentage / capital N. That N stands that I need a numerical value for whatever thing I have before. So if I pull down and say that, you see the answer will come to give you 7.41667. All right? So it's like a calculator. Now, but if I want to avoid using this second command, I will now go down to my input number 3. I will say N capital. I will now put a square bracket and dump all that I have inside. And then shift enter will give me that answer. So you use N as a numerical value to avoid the use of giving you square root of number or fractions. As we go on, you will see that. Now, you see pi, P-I, capital P and I. It's a number that we know that is 22.7. 22 divided by 7, is it not? Now, if I put pi, it will give me 22 over 7, which is a fraction. But once I put N with that square bracket pi inside, it will give me this. This is to 5 decimal places. It depends on number of decimal places I want. I move down to this. I say n pi, 7, which means I need the answer in 7 decimal places. Next slide. Okay, look at it here. You will see it. You see, this stopped at 9. This goes to 3. If I put 10, 20, it will give me to 20 decimal places. All right? That is one thing we know about pi. Yes. Yes, I will come to the use of the brackets. I will be able to tell you what those brackets are as we go on. That's a square bracket, yes. When I come, I will tell you the use of these brackets. I will tell you because you don't just use, like if I put n pi, for example, and say shift enter, it doesn't recognize it because we use the square bracket as an enclosure of arguments. We use it as enclosure of arguments. So we'll come to that before we continue. Now, Next slide. Okay. Just go on. Now, you see here, we have sine and always functions. Mathematical has all the functions you can think of. Sine, cosine, hyperbolic, exponential, natural logarithm, whatever is inbuilt. They are inbuilt functions. If I now come to say sine, the sign must start with capital S. And then you use a square bracket, which tells you sine has an argument. Sine x, sine x squared. Whatever that is there, we use a square bracket as what? An argument. After this, during the expansion, I will not tell you what each of them stands for. Now, if I say sine of pi by 3, pi by 3 is actually 60 degrees. Is it not? Okay. Now, if you execute this, it will give you square root of 3. My friend, have you installed your own? Okay. You should have done it yesterday now. Okay. Now, you will have this. It's still in square roots. The answer is not down to us. But if I say n sine pi root 3, it will give me the value. And that is exactly the value of sine 60.8660. Now, next one. Yes. Now, because there's a command, expand. N, for example, n. Now, see. They are all square brackets. Yes. That tells you n. You want to do this. So you want the whole of this that is involved in this argument to be written as a decimal. The real number. All right. Now, let's see. You can use it to expand. Like here I have 1 plus x raised to power of 10. That is, when you go on to learn it, there are functions, like in equation editor, that you don't need to use that. Like what I have, 1 plus x raised to power of 10. That is what is there. And we want to expand it. Expansion is an inbuilt function. So I will look at this. Expand. What am I expanding? It should be enclosed in this parenthesis, which means I must define my 1 plus x raised to power of 10. And I execute. This is exactly what that gives you in less than a second, depending on the speed of your computer. Because I asked you first, you do 1 plus x times 1 plus x, multiply by 1 plus x, and so on. It takes you a whole day. That's why we too that are coming from mathematics, we are lazy. Because we are able to develop things that helps us so that we don't waste the whole time. Okay. Now, we can also use that to factor an equation. For example, you have y equal to x raised to the power of 4 minus x cubed minus 2x minus 4. I want you to factorize it. It's a fourth order algebraic expression, which means there must be 4 brackets. Is it not? Factor will give you, these are the factors of that expression. Are you seeing that? Okay. Now, let us come to the use of these brackets, the way they are. There are 3 brackets that are actually important and must be used. This one, we call this one brackets. Most times we call it square bracket, is it not? Eh? This what? Is what? A square bracket, is it not? Eh? It's a square bracket. We use it. This is used to enclose arguments in our computation of a function. Let's say such as, if you want to look at cosine, we write cosine x, is it not? Eh? This is your cosine x. Mathematical does not understand what it means. Mathematical sees it as cos times x. So how do you treat it now? Because the argument is what? X. So this is an equivalent in mathematical as cosine. The C will start with capital this, and then you enclose this, and you put your x. That is the real representation of that. That is why we use the square bracket to enclose our arguments during computation. Now, you can also say e raised to power of x is an exponential. The way mathematics understands it, the exponential is an inbuilt function, and that goes in this manner. You must use exp to represent your e, and then the argument is what? X. So I could also look at this, assuming I want e minus x squared plus y squared plus I omega t. That this is our expression. Now, how do you represent this in Mathematica? You will see that D is an inbuilt. So you will start with exp, and then you must enclose it in a square bracket. Now, that will be minus of x squared plus y squared. I have this here, plus I times omega times t. I must close this. So this is the same as this expression. That's the way Mathematica can now use it to do a computation for you. I hope we are getting the concept. If you have any question, do not hesitate. Yes, you can also use it as small I, but the small I could be taken as ordinary I, because the imaginary number is understood in Mathematica as a capital I. So each one has its own syntax. Every high-level programming language has its own syntax. In fact, I will give you a book, Shum series. You can easily download it, but I will send you so that you don't burn your credit, your data. Okay. So, you see how it is. Now, the other bracket, which we call parenthesis, this bracket is called parenthesis. I hope I'm correct. There should be TH. Okay. Now, what it does is used in grouping. Is used in grouping. Mathematical expressions. For example, I want to have, say, x squared plus y squared multiplied by 3xex plus sine x, for instance, divided by, okay, sine of cos x divided by 3. You see how it is? This times this. So that is why we use the grouping. And that will give you x squared plus y squared multiplied by 3 times x multiplied by exp of x. I will close it, then plus. I will open it because there are two things. Each of them is divided by 3. So I will have sine of x plus cos of x. So you have to be careful when you are using division. Grouping matters a lot. Otherwise, you will not get the right answer. Once you divide the way it is not supposed to be, you will not get your right answer. Then you commit a semantic error. I hope people did programming. I think I'm correct. Semantic. Yes. You have syntax, you have semantic, and so on. Okay. Now, just like what you have here, you see, this is the use of these parentheses. They separate them. If you write this as minus 2 plus x into this, you have lost it. Is it not? It will just be like minus 2 plus the x is multiplying them. So it's no longer the same. So grouping is important with the use of your parentheses. Now, another one is what we call the curly brackets. Actually, next slide before I'll come to that because there's a use for it. Just the next page. Let me see whether it's there. No, go down. Go. I will get to, okay. Now, we can, don't worry, I'll write that before I come to. Go back to where you stopped before. Now, the curly brackets. What do we use the curly brackets? We call it braces. We call it curly brackets. They are used to form lists. They are what? Used to form lists in mathematical. They are very, very important. They are very important because they are a fundamental data structure. They are what? Fundamental data structure. So when you look at this, call it, they are very, very important. For example, you want to make a list of table. You want to plot a function. Say sine x. I want to define where the x values will be. For example, assuming I want to compute sign. For example, I want to table. I want to table sine of x. From which values? I need this. From x equal to, instead of equality, I'll put it from minus pi to 2 pi. For example, I will close. This will give me the values of this, starting from minus pi to pi. I can modify it. This one will give you this with a comma straight. But if I want to list it like a table, I could say table sine of x will go from x equal to minus pi to 2 pi. The next comma will give me the interval I want. Do I want in pi by 6? You see, that gives me, it will take, pi by 6 is what? 30. Is it not? It will take 30, 60, and so on until it's exhausted. For example, if I put, say, x, comma, 0, 30, comma, 0.5, means my step size is 0.5. Okay? Then I will close this and put this and say table form will give me the values like this. But if I don't put table form, it will give me this. So we use this for listing, which is very, very important. Now, we'll come back here. You will see some examples. Next. Now, you can also use Mathematica to make comments which are not used in computation. For comments, you can use it for comments. And what you do in comments, you put this parenthesis and put this and type like Dr. Lewis is the organizer. You close it. This is seen as a comment. You use it to refer as in documentation. After writing your program, you want to know whatever the axes are. So I can be writing, I say, I'm making an assumption that t equal to 1 here. I'll put it in this. This is not going to be used as part of the, but it reminds you, the reader, that this is what it is. So it's a comment. Whenever you put this and you close it, it's for comments. There's a way they do Fortran comments. How many of us use Fortran 4? How many of us have used Fortran 90? You should go to your programming, because most of the problems you are going to solve, people have solved them before. There is nothing that is new. The only new thing now is your ability to do some analysis. And some of these analyses are coupled with computational analysis. How many of you have heard about Python? How many of us use Python? Not the one that is inside that they are building. Okay. So it's good that we learn a little bit of programming. I have a student, the guy is a colleague in the department. He did his PhD with me. So I taught him part of Mathematica to do our program, and he is helping me to teach computational physics. And then the language he uses is Python. So we try to write Python. I have another student of mine. He works with C. C++. There are also one we published a paper last year. He uses a JavaScript. So you need to learn a particular high-level language. If you know how to do any of them, I could give you the problem, you do it with that language. It's a new thing, as Prof told you today. You need to do a new thing. Okay, so we'll go on. We can use as a comment. Like I said, comment. Mathematics can do calculus. Now, all these ones we are doing is just the bypass. Where we are going to now is what? Calculus. We use it to do calculus, differentiation, integration, solution to differential equations. And we begin to do plotting. Okay. Now, I have D, I have Y. For example, Y equal to x raised to the power of 5. I want to differentiate this. What will be my answer? 5x4. Is it not? Okay. Mathematica has an inbuilt differentiation. If I put capital D and I put in parentheses x raised to the power of 5, comma x, I am directing it to do a differentiation with respect to x. If I put t there, comma t, it will not give me any result. Rather, it will give me a null point because there is no t in the expression I have given it. Are you following me? Okay. Now, we can also use it to integrate. Integrate means you type integrate. Usually, all the commands starts with capital letter. Integrate. Integrate sine of x, comma x. I want the argument there is what? X. I'm integrating with respect to x. And when I integrate sine x, I will have a minus of cos x. What did I say? When you want to execute, what do you do? Shift, enter. Aha. So once you type this, now I want, you see where the curly bracket is coming now. I want to integrate that on a particular interval. That is called what? Definite integral. So what I have in the second integral, that is input 13, input line 13, is telling me to integrate sine of x dx from 0 to pi. That is exactly what that stands for. So you can use it to do your definite integral. You can also use it to do your what? Indefinite integral. Like the first one is indefinite. This is indefinite. And this is what? Definite. Okay, let's go on. Now, I want to integrate integral e raised to the power of x cos x dx. This is actually done by parts, is it not? Have you forgotten your integration by parts? That says integral of u dv is equal to uv minus integral u prime of dx. You have dv by dx of dx. Am I correct? No. You must differentiate your u here, which is actually your du by the x multiplied by v. V. I shouldn't put this. No, now, what are you integrating? Huh? Okay. Now, if I integrate that, you see how EX, I write it as ESP, X as the argument, multiplied by cos. The argument is what? X. And I need to go from 0 to pi, which means this is 0 to pi. It becomes a definite. Now you will see here, am I the one who did this? Okay. Okay. Today is working though. Now you see, this will give me this. But if I didn't put this, it will integrate it to give me what the value should be. But because I'm looking at it from the numerical point of view. Now, you see, it has given me the solution. I have e raised to the power of pi. But I want the value. I have to put n of this. It will give me this value. Are you following? So, that is the power. Now, we can also use Mathematica to plot functions. You can, yes. You can do it, but it looks cumbersome to the eyes. When you start using it, it will give you whatever it is. Then you want a numerical. It's also, there's a syntax there that will give you that. All you need to do is to put %n. It will give you the answer. You start drinking akamu before you start eating eba. No, be so. What do you do differentiation? Do you need to know the value of differential? That is numerical value. When we come, we also know that we also do it. But you must define, like I said, you want to differentiate x. You want to differentiate d by the x of x raised to the power of 7. And you want to know the value. What will it give you? It will give you 7x raised to the power of 6, is it not? Huh? Now, if your x is 2, you will come here, the next one, and define that your x is equal to 2. So, which means there's another line of statement you are going to beg. Then it will compute this, giving you this. When x is 2, it becomes 32 times 7. Okay? So you don't just begin to use your teeth when you don't have your teeth. Okay? Now, we can use Mathematica to plot. I have a function that I needed to plot. I have x squared. Say you have y is equal to x squared. I want to plot this in a region where x goes from -4 to 4. We can say x is an element of -4 and 4. So which means that is our line, -4 to 4. X is parabola. That is why it's a parabolic function. So, in that place, simply say plot x squared, comma, the curly bracket, x starting from -4 to +4. What will it do? The result will give you this. Are you seeing that? Because if I'm giving you this, first of all, you make a table and put the values. Then you begin to plot. But all you need to do is to write this, and it will just give you that value. We can also plot more than one graph on a particular graph sheet. Like I did here. Plot x squared plus 1, comma, x raised to the power of 3. X going from -3 to 5. Table. I want to table the results in a space of 5 so that you'll be able to identify which graph has whatever value it has. So that will give you. You can see the one on yellow is the one that has x raised to the power of 3 because that is the nature. And then you will now see where two of them could meet. So you will see this is beauty of the whole thing. So the first value there is that and that. Mathematica can give you this, and they will appreciate it. Okay? Mathematica has a lot of inbuilt functions. You have to follow the syntax. As I sat down there where he was delivering his lecture, was when I was writing this. You create it, that's what makes you. Now, you see, let's look at, you see the whole values. So you'll be able to see where two of them have the same answer. When you go through there, you'll be able to see where they cut each other. Now, there is what we call table. See, you can make a table. Assuming you have gotten some functions, you want to list the table. That curly bracket helps you for listing. Like here, I have table x squared plus 1. X from 0 to 10 in space of 1. It will just list the table for me. Are you seeing? So, for example, when x is 0, the value will be 1. When x is 1, the value is 2. When x is 2, I have 4 plus 1. When x is 3, I have 9 plus. You see how it goes? So that is listing. So the rest, after that, I will save this document as PDF and give you. Mathematica has that ability, but it has to also be defined and according to its. But instead of doing that, you can do that table because in Mathematica has ability to do statistics. When you go to the library, you will see it. I mean the library inside. Yes, I'm not talking of your main library. You can extract. Yes. Yes, you can. Because you can import, you can export. But now it will take you time for you as a beginner now to begin to use that. Most of the things you will do that I've been doing I have been doing. There are other software that can help you too that we use, that can help you assess where you have a read time, particularly those who are in observations. You can use that to get your data and store. So it's not all the software. If I take the documents I have here and export to Word, except I am very careful the way I present it, you will not get the real thing. And when you import, you cannot import the real thing. So because there are different systems, there are differences in documentation. All right. So that is the table. This one, we are making it in step of 1. So that's what we have. Now, Mathematica can also help you plot a 3-dimensional graphs. It can also make you to plot contour graphs, parametric graphs, all of that. It now determines how good you are and how you can lay hands on inbuilt functions. Like this, I will not go too much. I have to plot a 3-dimensional graph of x squared, okay, within that range. You see what it's giving me? Move to the next one, you will see the contour. Okay, these are 3Ds. You see, this one, because the intervals are not the same. That's why you have a flat here, is it not? At the top. The next one, where you have the same range, which means this is symmetrically represented. See the word symmetry? Turn it this way because they have the same. Now the next one is the contour. You see, this is the contour. If I have started with 0, it wouldn't be complete circle. It will give us a half. So these are things we can all do with our Mathematica. So when you see some of the graphs I presented, I plotted them in Mathematica and exported to the document by using a sniper tool. Do you know how to use sniper? Not the one that kills Anto. Whatever you call it. So you can use it to move the document. So you don't need to take it to, like this man. It's like you know how to use Excel. Some of my students want to copy this data and go to Excel, plot. Excel will not give you smooth. You see, but this gives you a continuous function because the functions are continuous. When you want to do a piecewise, which can create some discontinuities, like when you go to some functions that are discontinuous, you see them too. You know, discontinuities and singularities. Okay, so we can use this to solve equations. Like here, I want to solve x raised to the power of 3 minus 2x minus 4 equal to 0. And then I solve it, I have this result. Straight. It wouldn't take you 2 seconds after imputing the value. But see here, this is a quadratic equation. I solve it, x equal to 2, s equal to 3. This one gave us the solutions to be complex. It's what? Complex. It's only one that is completely real. The rest are what? Complex. But if you find the magnitude of each of them, the norm, you will now begin to see that this is 2, and this also 2. Okay. Now, let's look at something. Can you raise this up? I want to. Aha. Now, you see here, we have solved this problem. Depending on the mathematical you are using, you see these signs here. It's telling you that these are not actual signs. They have gone to interpolating polynomial. And it needs to do some more interpolation before you get the accurate result. But we can avoid this. Next one. All you do is to put, come now, come, a little down. Here. Now, if I put n solve, I need my solutions the way it will give me. You see, it has given me this. That is 5 roots. 1, 2, 3, 4, and 5. So you see the power of some of the centers. You will get it. You can also use this. I don't know how many of us who know root finding. Did we do numerical methods? How to use Newton's iterative, Newton-Raphson. Whatever you call it. Newton-Raphson is called find root. It's root finding. So I have cos x equal to x from x up to 0.9. I just put that. I will get the value immediately. So we use this to find root. Because sometimes when you want to solve some problems, you will get an equation. And you needed a particular root to advance in your research. Like I think Prof was telling you, you solve a problem, your own. You want to compare it with the previous one. What do? You put that value equal to what? 0. Is it not? Whatever additions you have, you remove them. See whether you achieve whatever the other people have. In some of them, you'll be able to find the root, particularly when you are looking at stability problems. You want to get critical points. Most critical points are found by what? Root finding. So that's why you need it. Maybe next time I'll continue to work. We'll come over to normal root finding, which helps you to find the critical points of a particular thing. Now, you can also move up. You can also use it to solve differential equation. You see, this is a second order differential equation like what we did yesterday. But the only thing now is that instead of here, I think this is a forcing. So it is inhomogeneous. This, you will solve this. When you equate it to 0, you get complementary function. And then you equate to this, you get the particular solution. Now, we use dsolve to solve this equation 1. And this is the solutions we get. It has how many? 2 arbitrary constants. But if you are given the initial values, those C's, C1 and C2 can be computed automatically for you. That's where we will start next class, so that we don't go too much. All right? Any question? Yes. D, everything starts with capital. Only D. But now we want to look at dsolve. D will start with capital D. S will start with capital S. Because in the centers, solutions, solving starts with capital S. Now you want to do 2 things at the same time. You want to solve this differential equation. It must be what? dsolve. Like I also have ndsolve. There are, well, maybe Dr. Lewis will do that one. When you have systems of differential equations, Most of them you may not have the analytical solution. Rather, you have a numerical solution. You will use what? ND solve. We'll come over to that, all those as we go on. I think here we'll stop for now. Let's have a small break. This is your paper.